main technological advancement of these companies. So, for example, in the field of machine-to-machine AEs on IoT, there are, like, as you can see, several companies running that. Some advantages. Some advantages include that, for example, Orbcom is 100% dedicated to machine-to-machine applications, which means it's gonna connect satellites. Using the satellites, it's gonna connect different machines, different vehicles in the globe. The constellation size is around 52 satellites. Then interesting project is Hideous Wire. This is they're gonna use S-band spectrum to receive the data from from the Earth, and with that they're gonna do the frequency mapping. That's one of their application. Swarm technologies, they are based on actually like really small satellite sizes, which is 0.25 units. Gonna be dedicated to two-way communication with small satellites. Like, it's pretty crazy project, and they had like lots of troubles with frequencies. Yeah, I'm not like we'll see how it will go for them in the near future. Then Lacuna Space, for example, they're also providing machine-to-machine communication and so on. The second big trend, as you can see, is the Earth observation and Planet, launched since 2013 with total amount of 427 satellites. With sensors that they are providing, they can go up to 3.7 meters ground resolution with quite a big swath. And the major satellite altitude is 475, which means that satellites decay within like a year or several years, which makes it for them necessary to launch other satellites to have the full constellation kind of covered. Regarding Earth observation, there is also Reactor Space company. They're doing hyperspectral imaging besides normal imaging, and yeah, Hera and so on. If we see on the third most popular application, it's like weather, AIS and ADS-B. For example, this is for Spire. They're measuring the GPS signal. That's I think what we've also had a quick chat before. So I mean, that's a little bit other technology, but close to that. Changing in GPS signal passing the atmosphere and predicting the weather, how the weather is going to change regarding temperature, pressure, and humidity. Then Harris Corporation is also dedicated to weather monitoring with 12 satellites. They would like to map winds in 3D over the Earth. So, and orbital microsystems, for example, they also aiming to capture the temperature of the Earth, so that they're going to map the temperature around the globe. And Unseen Labs, for example, interesting applications, the RF spectrum monitoring. So that means that I think the major application field for them is to search for illegal ship fishing and illegal activities in the ocean. Basically, if there is an illegal ship in the ocean and it emits some radio signals because it needs to have some means of communication, and with the use of the Unseen Lab service, it would be possible to detect the plate and position this illegal vehicles and more precisely like ships. Yeah, so there are some like really exotic applications, for example, like optical communication. SpecuTrail, the company has been just announced they're planning to launch their first satellite in this year. They did not decide upon the constellation size. However, they're aiming to provide quantum communication, like really secure communication using the small satellites. Yes, all right. That was regarding some commercial CubeSat applications. I think the cool thing is to see the crowdfunding numbers. There were a couple of nanosatellite crowdfunding campaigns. Actually, there were quite a lot, and we can see how the goals were achieved. So, for example, me personally, I like the Andurasat the most, I think. So they raised 100,000 K for building the satellite based on Arduino platform, and they have launched it. The satellite was working on orbit, and since then, like after the successful launch, the company shifted to other markets and became Spire, and now they're having their own constellation. I think the most successful was Arcade from Planetary Resources, was $1.5 million in 2013. Yeah, to take selfies from space using the small satellites. Like, okay. Also, like, pretty exotic application. Then yeah, you can have a look afterwards to different crowdfunding campaigns and to see how crazy can be people about the applications of small satellites. Regarding technologies, I would also like to show a little bit of some advanced technologies small satellites are carrying. Regarding communication, there are quite a lot of companies providing communication services and giving communication payloads out. So there are a lot of advanced instrumentation from NASA, especially for interplanetary CubeSat missions. As we talked about this Marco satellite, it was carrying the huge X-band panels with almost 30 dBi gain for deep space communication. There are also like other types of high-speed communication, which K-band, X-band, which can achieve up to 200 megabits per second and 500 megabits per second. Right now, there's also a hot topic for small satellites, the optical communication, and there are, I don't see them here in the table, but with the use of optical communication, it's possible to achieve like gigabytes per second. And for small satellites, this technology is still under development. Power-wise, some advanced deployable solar panels or some advanced lithium-ion batteries. Also, like, you can see some examples of different payloads and different instrumentation. Regarding propulsion, there are also quite many companies which have been founded last years, which are working on like different types of propulsion with different propellant. Like in general, starting with non-propellant like solar sails, or like nanotrusters with liquid metal or electrosprays. All right, so that's like, I highly recommend this source. You will find like a lot of data for inspiration and for like in general, if you want to know more about the missions, about companies, and about like the background. That's the really nice database for that. And I'm going back to the presentation. Yes. And we start with Cubesat Design Specification Revision 14. I hope it's not going to be too boring because we're going to talk about requirements and standards. The Cubesat Design Specification is basically the document which describes what guidelines and what requirements shall the satellite follow. It's not as defined as might be a document for a bigger satellite. However, like based on my experience, some customers still can get some troubles with these requirements. And I will tell a couple of fun stories in the end of this session regarding the troubles. All right, so there are some of them general requirements. So the first one is basically Cubesat shall incorporate some like shall submit some reports in terms of following these requirements to the launch provider. Yes. So all parts shall be remain attached to the CubeSat. It's not possible that something is being deployed while the launch. There shall be no pyrotechnical devices inside the satellite, and the satellite shall not generate additional space debris. No pressure vessels over 1.2 atmosphere shall be inside the CubeSat, and the safety factor shall be more than 4. Total stored chemical energy, if we're talking about like batteries, shall be less than 100 watts hours. Satellite shall not include any like really hazardous materials. Satellite also shall satisfy the following, like this outgassing material, that total mass loss should be less than 1%. And regarding this, most of the CubeSat providers are doing the bakeout during the satellite testing and satellite preparation. That happens like in an environmental chamber where the satellite is baked, and what can get outgassed gets outgassed. However, this requirement might be even tighter for some optical communication, like optical payloads. But that's already on the side of the payload provider. So that's like their business and their problem. Collected volatile considerate material shall be less than 0.1%. And that's basically that's all written in the specification. There are a couple of things which are required to have in mind. That's the coordinate system orientation. That's the one of the main ones. Configuration and physical dimensions. This is the place where some of the CubeSat have problems. They shall really follow the dimensions, otherwise it might not fit into deploy or might be too loose in deploy and it will be shaken during the launch. So on the 1U side, it shall be 100 millimeters wide, and the tolerance is plus minus 0.1 millimeter. Basically, this is the dimension between like major rails. Then the single dimension is already 113.5. Triple is 340.5, and there it's a little bit bigger the tolerance. Regarding the components which are expanding from the rails, there is a place of 6.5 millimeters where some additional instrumentation, like sun sensors, or payload sensors, or some deployable sonar panels can be stored. External components shall not contact the deployer, otherwise the satellite might have troubles during the deployment. Rails is the main mechanical interface between the CubeSat and the deployer. And basically, from the mechanical perspective, the most tight requirements are put on these rails. So their minimum width shall be 8.5 millimeter. It's really important to have correct surface roughness of less than 1.6 micrometers. Otherwise, there might be some unnecessary friction between the rails of deployer and the rails of the CubeSat, which might also make it difficult for the satellite to be deployed. Edges shall be rounded at least 1 millimeter radius. Z plus axis shall have minimum surface of 6.5 over 6.5 millimeters square. At least 75% of rails should be in contact with the rails. That means that if satellite is too small and is too loose in the deployer, it's also not acceptable because of the internal vibrations of the satellite during the launch. 25% of rails may be recessed. That's about rail contact of single and triple satellites. Regarding the mass, single CubeSat shall be less than 1.33 kg, while triple CubeSat shall be less than 4 kg. And based on my experience, it's really hard to make them be harder than that. So as most of the components in such small satellites are electrical, like PCBs do not weigh more than total amount of printed circuit boards cannot weigh more than 1.33 kilogram for single CubeSat. Center of gravity shall be located within 2 centimeters sphere around the geometrical center of the satellite. This is kind of pretty hard to track, this requirement. However, when the overall launch vehicle ballistic analysis is conducted, this requirement is taken for the overall launch vehicle as a basic. It's not so strict in reality, and some deployers can handle a little bit more of this deviation. However, if all the satellites will have in one container, we have geometrical center deviated to one side, that might become a problem. So it's better to keep the gravity in the center of the satellite, especially when we're talking about active attitude control. The closer the center of gravity, the center of mass to the center of gravity, geometrical center of the satellite, the easier it is for different maneuvers to be conducted. Regarding materials, aluminum of 2 alloys are the most common for structure and for rails. For structure, aluminum 70-75, and for rails 60-61 is used. Rails and standoffs shall be hard anodized to prevent cold welding. In other words, we do not want the satellite to stay in the container due to the welding. That's why there shall be no conduction between these 2 components. Separation springs shall be on designed rail standoff, shall be placed either on the side of the rail or in the back of the rail. This separation spring, basically is the one which is touching the rails during the satellite deployment. And it also has to have some defined 0.05 inches above standoff. And this is not a really tight requirement for 3 CubeSats. It's more for it's for 1 unit CubeSats when they're together, in 3 unit deployer. The separation spring helps to separate the CubeSats one from another. Basically, maybe I will repeat it once again. For 1 unit CubeSats in the 3 unit deployers, all these 3 CubeSats are accommodated inside this deployer, and there is a separation spring between them. So these are the requirements for this separation spring between. And as the 3 CubeSat is occupying alone all the space in this deployer, there's no need for these additional requirements. All right, this is the basic drawing for the 1 unit CubeSat, which every CubeSat manufacturer shall follow. Here, basically, you can see the sizes, geometrical sizes, the tolerances, and so on. From different perspective. Basically, rails, contact rails for on the sides, the places for deployment switches. The red ones are the deployment switches, and these ones are separation springs. A few words about deployment switches. So basically, when the satellite is in the deployer, it shall be powered off, not to influence any other instrumentation on the launch vehicle or in the deployer. Basically, these deployment switches are aiming to shut off the battery from all the satellite. And they work in the way when the satellite is in the deployer, these two deployment switches are pressed. And as soon as the satellite is deployed on orbit, they are pressed. And by that, battery is connected to the main electrical power system and satellite is turned on. All right. Besides the geometrical, main geometrical dimensions, there are also two access ports located on the both sides of the CubeSat. What are these access ports? Basically, after the satellite is installed into the container, it is still possible to get an access for last verification, last checks on the launch side. For that, one of the windows of deployers can be taken out. It's a small window, and with taking out this window, it's possible to get an access to this green area. It is possible to place here, for example, the connector. We call it EGC connector, electrical ground support equipment, and to make last preparation of the satellite, which is charging the batteries, checking the software, checking the state of the systems, and so on. So yes, this is the major CubeSat specification from mechanical perspective. This picture is also taken from the Cubesat design specification, explaining how big in units can CubeSats be. And from here, we go into some electrical requirements. They're not so many, but still there are some to remember. There shall be no active electronics during launch. So battery or CubeSat with battery shall be fully deactivated or discharged. Discharge is not the best idea. Probably most of the people, most of the CubeSat developers want the satellite as soon as it is on the orbit to start working and to start functioning properly. For that, the CubeSat battery is detached using these deployment switches I've just talked about. For that, minimum one deployment switch is in designed rail shall be placed. So the best is to have two deployment switches on two rails. All right, to bring some kind of redundancy, and in terms if one deployment switch is failing, this is a really critical requirement. So it's better to have some additional instrumentation for that. And during the launch, all systems shall be turned off, even including real-time clocks and everything else. Yes, to allow diagnostic charging, all connectors shall be at access port locations, and this is this requirement is about this access ports. Basically, if you want to follow, if you want to have an option to get access to the CubeSat, you can follow this. If you think it's not as important, it's possible to ignore this one. However, there might be some situations on the launch side when it's better to have an access for the satellite. CubeSat shall include remove before flight pin or be launched with discharged batteries, which is in most cases not the best idea. Remove before flight pin shall be removed after the satellite integration into the deployer. So basically, how it occurs, the satellite on the launch side, or for example, once our customers bring satellites at our facilities, the satellite is turned off. And as we have noticed, there's a way to turn on the satellite pressing the deployment switches. There's also another way of separating the battery from all the satellite subsystems is using the remove before flight pin. Basically, it has the same functionality. It detaches the battery from the system. So once the satellite is ready for integration, the remove before flight is installed. Most likely it's actually installed during the transportation, because like we don't need the working satellite during transportation from the customer's facility to ours, especially like we don't want to consume the battery or the satellite to operation on Earth. Thus, after the satellite arrives to the integration facility, it's been like everything was prepared, satellite is integrated, satellite is turned off. Then the door of the container is closes, and at this moment it's important to not to forget to remove before flight pin. This is done through this access port location. Yeah, so it also cuts all the power from the satellite, and remembering the requirement, like mechanical requirement from this 6.5 millimeters extrusion from the rails, it shall also not be higher than that, in order to get like satellite into deploy with remove before flight pin installed. Some basic operational requirements: Cubesat with batteries shall be able to be shut down by transmitter command. This is in case there are some troubles or there might be some legal troubles. For example, with this 0.25 unit swarm technologies, there was a big story when they did not file the frequencies correctly, so they had to be shut down because they were not following the specific rules to get this frequency allocations. So there shall be some kind of tool to shut down, or to shut down satellite with the command over radio. Deployables shall wait until at least 30 minutes after ejection. This is also the safety rule. While after the ejection into the orbit, there might be like that. So the satellite is not the only one deployed. Normally, like 10, 50, or like 100 small satellites can be deployed more or less at the same time. And if some of the satellites had like a really big deployment, for example, a sail or like a big boom or antenna or solar panels, and not enough time has passed for satellites to get spread, there might be some collision. So it's better to wait for some time until satellites are a little bit spread in the orbit to conduct this deployment. The same is connected to radio frequency transmitters. So all the transmitters with power more than 1 milliwatts, which are basically all transmitters, shall wait at least 30 minutes after ejection. This is also, this requirement is also not to damage the transmitters of like other satellites while like right after the deployment the satellites are pretty close and pretty dense to each other, and after 30 minutes they can be already spread. Operators shall obtain and provide documentation proper to frequency licenses. And if we're talking about amateur frequency licenses, as UHF, which is I think the most used frequency for small satellites, there shall be a proof of coordination by IAA-RU. And some companies, as I just mentioned, can have troubles with that. It's better not to play with frequencies. Orbital decay time shall be less than 25 years after end of the mission. And that's like, obviously nobody's also gonna, like it's pretty hard to estimate how, it's possible to calculate how fast the satellite will decay. And this is, decay lifetime is a critical requirement once we're talking about the space debris. Having in mind the amount of satellites which are planned to be launched in the constellations within upcoming years, this might be a critical requirement for the next missions. Yes, so regarding the fit checks and deployer integration, there shall be a final fit check before the launch. And basically, like our customers are bringing satellite dummies in our office before the final satellite integration into deployer in order to fit check the geometrical dimensions. And sometimes it happens that the satellite is not fitting due to like this dimensional differences between requirements and actual sizes between the rails, which is kind of pretty sad. At least if it's done before the final satellite integration, it's possible to like still change some rails dimensions and like either reorder the structure or work the structure out. For that, Cubesat acceptance checklist shall be used, and this checklist you can find in the Cubesat design specification documentation. Regarding the testing must confirm all launch provider requirements, and this really depends on the launch vehicle, as different launch vehicle have different loads, different like vibrational profiles, and prior to the launch, like it's important to check them out. At ExoLaunch, we are also providing the test service. Basically, the satellite can be delivered to our facilities, and we have partner companies here in Berlin where with like big shaker tables where it's possible to conduct tests with all the launch providers we are working with. Right. If launch vehicle environment is unknown, there is a standard which is used for testing requirements. And regarding testing requirements, it's also, I think, important to mention that the satellite itself shall not strictly follow the requirements, like the vibrational requirements of the launch provider, as the satellite is placed into the deployer during the launch. The deployer takes most of the loads for itself, as the satellite is fixed in the container in the deployer. So the deployer, this connection between deployer and the satellite, it dampens some of the frequencies, and it changes the frequency profile with actually like bringing amplitudes of frequencies, like amplitudes of vibrations lower. So there are different tests which are called like acceptance tests, protoflight tests, and depending also on the launch vehicle, it's possible to conduct like one of those tests prior to launch. A few words about specifics of Cubesat missions. So university Cubesats are usually designed within 3 to 4 years. That's enough time to conduct the research, to build the platform, or to buy the platform, to conduct all the tests. And 3 to 4 years is, for some student projects, exactly the time where like during the bachelor or during some years of the master, students can like participate and to observe the biggest part of the mission. So undergraduate and graduate students participate actively in the development of the satellite during these 3 to 4 years. Commercial CubeSats are usually designed from 1 to 2 years, and that depends really on if the company has the platform, or does the company need to modify the platform for a specific payload. And typical teams consist of like 18, 12 engineers for an average mission. At least partially CubeSats, at least were designed from scratch. And I think today there are like just so many companies providing platforms and providing solutions which are ready. So there's kind of no need anymore to design the satellite from scratch. And especially for the university, I think it's much more attractive to come up with some advanced instrumentation and advanced or like interesting payload, and then just buy the platform which has been flown, which has shown its reliability in past missions, and like maximize the scientific outcome by focusing on the payload design than on developing like some new CubeSat platform from scratch. Yes, so more than 60% of all CubeSats that reached orbit remained operational for more than 6 years, even though the design lifetime is 2 years. This shows that most of the CubeSats that are failing like either from the very beginning or not failing in a long time. Like low Earth orbit is not so aggressive regarding the radiation. There, like it still is, but most of the commercial components can successfully work for a longer time than just 2 years. All right, then we jump into the CubeSat design philosophy, and here we're gonna talk about how do we work with CubeSat projects, and how do we address the question of building the CubeSat like platforms. There are kind of two types of philosophies. First one is to design to objective, or the second one design to cost. First one is based on the goal of the mission. So if you first come up with the goal of the mission and the goal of the payload you want to have on the satellite, and through the first things to determine is expected environmental conditions. On that stage, already hardware shall be appropriately designed and selected for mission objectives. And new designs must be generally tested against environments. In this case, time might not be the critical parameter. However, not as in the second philosophy, where design to cost. Here, the project cost is fixed, and with a fixed cost, the team shall define what is possible to achieve, which objectives and which goals. Components selection is normally driven by costs, not as design to objective, where it's possible to choose like hardware which is deviates maybe in terms of cost from the minimum like budget. Mission objectives and requirements are often subject to change due to affordability. Few words about design to objective. So at the beginning of the project, we have the mission idea, which is later in the program segment split between mission objectives and mission constraints. As constraints, there are costs, resources. There can be also like availability of engineers, or like ground station infrastructure, and so on. From the mission objectives, there are two types of major requirements. First is operational. The second one is functional requirements. Operational requirements include like mission operations, and this is connected to like ground station infrastructure. Functional requirements include orbit. Do we use a constellation? Which are orbital parameters? And so on. So that's on the program segment. All of these questions are announced. So orbit, constellation costs, and some other constraints, they bring us to the launch element, and here the launch vehicle, the launch type is selected. Orbit and constellation also, and all these constraints, they also define the space segment. Here we define what the size of the CubeSat shall be, what are the main parameters in terms of electrical power, in terms of like communication requirements. And with this satellite space segment defined and with mission operations in mind, we need to define a communication architecture, and this involves the ground station architecture together with mission control, and so on. That's this is the approach while designing, having the objective in mind. Yes. So that's yeah, maybe like a few words. When we're talking about design to objective, we of course have this, like, we cannot define it without having the cost and other requirements. And most likely, like the launch element is selected a little bit afterwards, while in the design to cost, cost is the major driven requirement, and launch element, as we discussed earlier, it can be like pretty much the half of the satellite cost in the end. It's a big question to address, so like in the very early stages of the design. So this design to cost became one of the most used and one of the most like basically most of the projects regarding CubeSats are driven by design to cost methodology. And radical cost cutting can actually reduce the system reliability and performance to the level where it's actually dangerous to, or like, not dangerous, doesn't have sense to launch the CubeSat. There are a couple of components which is better not to cut costs on, which become the most expensive parts of the satellite in the end. These are the solar arrays, and even lowest budget missions, they use space qualified solar cells. Yes. Regarding the batteries, battery is one of the most risky components, and it's also due to like environmental conditions, the temperature there can get like pretty low, which is crucial for batteries operations. Thus, it's also necessary not to cut costs during the batteries development. And communication system is the third crucial component, where it's better to invest additional resources into the development to have stable communication line with the satellite. Quality assurance while designing to cost methodology is actually also a critical component of the overall design. So it's better not to save too much when it comes to quality assurance of electronic components design or software. So the interface control, mechanical testing are the most important things to do during the satellite development, and especially if it's possible to outsource some job, like for example harnessing development, it's better to do so to leave some space for more testing. Some approaches look more expensive, but some of them help saving some money in the end. So for example, buying subsystems can be cheaper than developing your own ones, and it can be also more reliable it can be better for the mission to buy some components which have been already tested and be sure that they will work on the satellite. So when you're designing the CubeSat mission, it's better to focus on the strength and focus on the goal of the mission, and to leave the rest for others. I would like to ask if you have any questions until now. Is everything clear, or?
Yeah. Questions do you have? So I think for now is okay. I think they are keeping their questions till the end.
Till the end. So do I understand correctly that the lecture is until 1, right?
Again, sorry? Lectures?
So the lecture until 1.
Until 1. Okay, European time. Yeah, you have.
One more hour.
Yeah. But you can finish earlier if you want. So there is no problem.
Okay, so we can make maybe 5 minutes break, and then there will be.
Of course.
The last part.
Because even the professor from Sofia, she asked 15 minutes. So because they used to like 40 minutes lectures, 10 minutes break. That's kind of how to say.
Yeah, standard.
Yeah, some
Okay.
kind of standard. Okay, no problem. If you want
Okay.
some break, it's okay.
So yeah, so like before the next part, we can make it like a 10-minute.
Yeah.
Okay. Yeah.
Thank you. So again, 10 minutes break, and we will start at 4. Sorry, it would be 12.
Yeah. Yeah, if you have any questions, please like put them in the chat and we can address before the next next round. Yeah, thanks.